All right. Hello, everyone. Welcome to the second session of the GDSE EXE course. Today, we'll be talking about API development in Go. We're going to talk a little bit about the language itself and how you can make backend applications using Golang. So, the intent of this session is to introduce both Golang and backend. People who have done backend before but not Golang will hopefully get a grasp of how the language works, and people who have started with Golang and not experienced, not they're not experienced with backend development, they can also understand how this works. All right. So, firstly, Go was designed in 2007 by Google, and version 1 was released in 2012. It's basically a blend of C and Python. It's statically typed, which means that you have to declare a variable and its type before you can use it. And it's also as performant as C, and it integrates the readability and usability of Python alongside it. So one of the best features of Go is also high performance concurrency, which we'll be looking at later in the session, and networking, which is backend applications. So many applications which are commonly used in development, such as Docker and Kubernetes, these are all developed by Golang as well. So it's a very popular language. It's very common, and it's very versatile as well. So in Golang, we have all our code, which is organized in packages. And a package is basically consisting of various functions which perform tasks. You have the main package, which is where the Go compiler looks to first when it's executing code. And you can also import packages from elsewhere. And these are all managed in the go.mod file, which also keeps track of the version of the package and everything, so that when you are running the code, you import the same packages and the same versions as they were when the developer wrote them. And this helps create consistency through the application when it was created and when it's being used. So we initialize a module with the command called go mod init. So I'm going to show how we can create a simple Go file. I'll create a directory here, right? And here I'll type go mod init. And over here, we're supposed to enter a module name. Now, the module name is meant to be unique. So generally in deployed applications, you'll see people use URLs which are unlikely to be used anywhere else, which means, so it'll most likely be a URL that they themselves own. So a common example is to use your GitHub. So we can do github.com/Aditya, and also our application name, so test, right? And using this, you can see that in our session, we have a go.mod file which has been created, which gives the version of Go 122, and the module is written over here. This Go 122 is the latest version of Go. There'll be a download link in the chat. Everyone can download it and set it up. It's very easy to set up. So this is how we create a go.mod package. And here we'll create a simple main.go file, right? So first, a main.go file, it consists of the package declaration, which is telling you which package this file is supposed to be in. And since it's the main file, it'll be in the main package. And here we create a main function, and we print in hello world. So what we can see here is that the main function, similar to how C, C++, and other languages work, the main function tells Golang, the compiler, where it wants to start the code and where it should start running from. FMT is a Golang inbuilt package, which is used for input-output. And this is an example of how you can import packages into your code to perform functions, right? So the FMT function is also, it's properly documented. You can see it all over here, right? So this is how hello world works. And we'll also talk about some of the other main parts of Go, such as variable declaration. And variable declaration in Golang is slightly different compared to most other languages. Usually in C and C++ and stuff, you'll have int c is equal to 10 with a semicolon. That is not how it works in Go. In Go, how we declare variables is we type the keyword var, and we give its name first. So var hello, and then we give the type later. So this is something that you'll see in Go often, that the type of the variable is often given after the name. And so what we can do here is we can say hello is equal to hello, right? So currently it's giving me an error because I'm not using hello anywhere. But if I were to change this, then this was this error goes away. Now, the way we can run Go files is within this directory, the session directory, we'll write go run and then dot. And dot means run the directory that we're currently in, right? So, one second. Right, so we can see that hello was printed as we intended it, right? Now, what will happen is that this can be converted into a shorthand form. So instead of making it, instead of declaring the type here, we can also say that hello is equal to string. And this, and this operator here, this colon equals to, is the Golang shorthand form for declaring variables. You don't have to give the variable type. It'll automatically detect that, and later you can use it as you will here, right? So we're going to talk about stuff like for loops and functions now, because these are stuff you'll often see both in advanced Go and backend development, right? So the way for loops work is you declare for I is equal to 0. This is the declaration, right? I less than 5, I plus plus, right? And here you have to use the brackets, which declares the block of the for loop, and we'll do fmt.println and print I over here. So when we run this, you can see 0, 1, 2, 3, 4, right? Now, another thing is functions. Say you have a function over here, which is saying to print hello, right? And the way functions work is similarly, you will have parameters, and similar to how we declared variables, you'll have function parameters declared as their name first, and then the type. And then you'll also print what we want to return. So here we're not returning anything, so we're just going to leave that blank. And we're going to copy paste this line into this. And we will change this to hello, right? So we also want to now comment this. It's going to give me an error because I'm not using hello anywhere. And we want to call the print hello function and give it a name, right? So again, we got 0, 1, 2, 3, 4, and hello, Aditya. Now, one other extremely important thing that you learn in Golang is the ability to declare methods as part of a type. And what that basically means is that you can create a custom type here, right? So I can say that type hello is a string, right? And so this actually creates a custom type called hello, which is basically implementing a string beneath it. But what we can do now is we can implement a function on this type. So what we will do is we will say hello, and we will create a function print. And we can say that, okay, what we want to do is println hello, and then h. So this h is going to reference the type that called it. So if we were to make a value, for example, name is equal to hello Aditya, right? And we'll change that to colon. Now we can say name.print, right? So here, name is actually of type hello. You can see Earlier, it was saying over here, name is a type.string, and this is a different name. So don't get confused on that. This name here is a type hello. And this type hello has a method declared with it called print. And what is happening is that it's calling this print function over here, and it is now printing hello Aditya again. All right. So this is some of the common stuff that is required in Go. And with this, we have a basis for where we can learn how backend development works and how servers are made in Golang. Right. So firstly, we need to talk about HTTP requests, right? So the internet, how it works is that it consists of resources which are all hosted on different servers. And when you search for something, you are the client. You're asking their server for resources. And HTTP, or Hypertext Transfer Protocol, is basically a method of communication for clients and servers so that both of them are on the same page. They both know the language they're speaking. And so it's easy for them to communicate, right? You have a client here, it'll send a request to the server, and the server will then respond to it, right? So what is the structure of a request? It consists of multiple parts. You have the URL, which is the Uniform Resource Locator, and that's basically a unique identifier for the URL the server that you're requesting information from. It also consists of HTTP methods, and these can be of multiple types. Like get is to request items from a server, post is to send items to a server, delete, etc. And these all change the functionality of what the server is supposed to do when it gets the request. If it gets a get request, it's going to give you information. And if it gets a post request, it is expecting information from the client. It also includes HTTP headers, which are basically key value pairs, which consist of extra information that the server might want to know. And this can consist of authorization tokens. It can consist of the content type that the request has, and others as well, right? And then the body, which is basically data. It can be in JSON format, it can be a form, it can be raw data. Any data that comes along with, for example, a post request will come under this body. And you can see that we have a small diagram over here, which talks about the method, which is get. And this is the server name, the URL, https server.com. And path and query string parameters we'll look at slightly later. But we also can see it's mentioning the HTTP version, the host, the authorization. These are all HTTP headers which tell the server some kind of information about the request that's coming in. All right. And so the server, when it gets a request, it'll process that information, it'll perform some actions, and it'll send back a response to the client, right? The client wants to know whether its request has been received, whether it's been executed, if something went wrong, what went wrong. And all of this stuff is communicated to the client using HTTP responses, right? The HTTP response, it consists of firstly a response code. And this is a three-digit code, which will tell the client what happened to the request that it sent to the server, right? If it consists of either it can start with 1, 2, 3, 4, or 5. And here we can see the different types of response codes that a server can send. You have the informational response, which means that the request was received, but processing is still happening. Successful. Redirection, which means that further action is required to complete the request. A client error, which means that there was something wrong with the request that the client sent. And a server error means that while processing the information, there was something wrong in the server. Usually that means that there's a bug in your API or something similar. And we have a diagram of the response codes here. We have 200 OK. This is if everything is successful, this is the one that you'll be seeing, 200 OK. You have the URL, which was called, and different response headers, which is the content type, the date, and all that stuff. And if it's a GET request, the server will be sending back data to the client. So that comes up in the body over here, which is over here before it's cut off. And here we can see while you're sending requests, often you want to if you're getting data, for example, you often want to segregate what kind of data you're getting. And this is where query and path parameters come into play. They're used to give information to the server as part of the request, right? Not the body, but in the URL itself, we're trying to give information to the server. So, for example, a path parameter is something that shows up in the path itself. We have server.com/v1/movies, and here movies can be something else. For example, if it was asking for books, we would replace it with books. And a query parameter it starts with a question mark, and it has a key, and it has an equal sign and its value. You might have seen this if you ever looked at a URL of like YouTube, for example. They often have this question mark and equal sign combination, which gives a query parameter, right? And the question often comes up as to when we use path parameters versus query parameters. And generally, the rule of thumb is that path parameters are for grouping data and query parameters are for filtering data. For example, I gave you the example of movies versus books. And query parameters could be, for example, starts with, or if we wanted release dates, all that kind of stuff will come in the query string. And you can see over here as well, this path orders, right, API. These are all like path parameters. The query string created at is this timestamp over here. The limit is equal to 10. So this is used to give information to the server as part of its request. So we now come to what is an API, right? An API is basically, the full form is an application programming interface. And you as the client, when you request information from an application, you're not going to be talking to the internals of the application, right? So that's what the API is for. It's a thin layer over the application where the client can talk to the application, where it can send its requests and receive responses from. So the API is just the external part, which is exposed to the rest of the world, right? So this is how API, you can see this is a sort of diagram on how the API would kind of look like. And inside the application, we have what's called a server mux. And this server mux is basically responsible for retrieving the request and sending it off to a function for further processing, right? So depending on what request you send to the API is going to have routes registered to it, right? Which is basically, it'll be part of the URL. And each route is going to want to do something different, right? If you want, for example, if you want to get movies, you'll send it to a different route. If you want to authenticate someone, you will send that to a different route. So each route will consist of a handler, and a handler is basically a function, right? It's basically a function that is used to handle that route. Everything the route wants will be handled by this function. All the processing will be done here. It may call other functions inside it, but this is where it retrieves the route and gives you the response from. And the server mux is in charge of making sure that the correct route moves to the correct handler, so that you don't have routes calling other handlers and all that. So we're going to talk about how we can make a simple web application. So I'm going to delete all of this. We're going to add back package.main and our func main, right? So what we want to do is, first we want to create a server mux. So you can create a server mux by calling http.new serve mux, right? And so what this will do is this will create a server mux for you, right? Now, how this is going to work is that this, as you recall, is in charge of making sure that all the routes and the handles are being paired together properly. So if we want to register a route on this, we will say mux.handlefunc. And here we'll give the path. This is the route over here, that if any route consists of a backslash, it wants to be handled by this. For example, let's say greet function, right? This isn't there yet. We're going to create that. And what we'll say, we'll log that we're starting the server at localhost 8080. And then we'll also say http.listen and serve. And here we'll pass in the localhost 8080 and the server mux. So what's happening here is that first we're creating the server mux and we're registering all the routes on it, right? We want to register that this greet handler will handle this route over here. And once all of the routes have been registered, we're printing, okay, we're starting the server now at this port. And then we're going to start the server. We're going to call listen and serve. And we are going to call localhost 8080 and pass in the multiplex, this server mux. So that means that all requests that are sent to port 8080 will be handled by this server mux. And now that we've gotten that set up, we can create our greet function that we defined over here. So we'll say func greet. And each handler requires two parameters, right? It requires it requires two parameters. So firstly, it requires a response writer and an HTTP request. So what are these two parameters? A response writer is basically what writes to the web page, right? When you call an API, this is what's gonna, when you're writing information to the response, this is what you're going to call, right? You're going to send the information to this response writer and it's going to give the information to the response body. And the HTTP request is basically, it's a structure, right? And the structure is containing all the information that came in with the request, right? So it'll contain like the URL path, it'll contain any path parameters, query parameters that existed, the body, all of that stuff will be accessible through this structure. But currently what we're going to do is we're just going to say fmt.hello web. Right. Now, what is fprintln? Earlier we saw println, which basically printed the console. And fprintln is basically the same thing, except you also provide an extra parameter, which is the writer, right? Where are you writing to? Println by default writes to the console over here, but fprintln, you can choose where do you want to write it to. And so when we run this main.go now, we are going to get starting the server at localhost 8080. And if you were to click it and go to this, you can see here we have hello web. And one useful tool when you're developing is this network, this developer tools that Google Chrome provides. You can access it with Control-Shift-I. That's the keyboard shortcut. It might be different for different browsers. Google Chrome is Control-Shift-I. And you can see that when I call this request, it registers over here, and you can see all of the data here. This was the request headers, accept encoding, all of the stuff that's there. And this was the response, right? You can see the 200 OK. You can see the request method. By default, when you're calling a web page from here, from your browser, it'll usually be a GET request. But when you're calling from other places, when you're calling to an API, you can send in the type of request as well, as like post or delete. So now we're going to decide, now we're going to see, okay, how do we want to structure, how do we want to define the method that is being called on this route. So for example, if I had a /test and I said that, okay, I want only post requests to come on this test route, right? How would we do that? We can create our handler, right? And we can say that if our dot method is not equal to post, then we want to say this method not allowed. right? And if it is post, then we can say, okay, then it's fine. We're fine with this. And so you can end the server with Control C, run it again. And this time I'm going to use curl because, as I mentioned before, generally in the browser you have GET request. Curl is a tool that allows you to send requests from your console. And if you're on Linux, curl will be available like this. On Windows, it's usually curl.exe. So we'll do curl.exe and -i, which displays all the headers as well. -x is used to define what kind of method we want. And now we give the URL that we wanted, right? So now we can see that, okay, it's HTTP okay, and we see post was accepted. Over here, you can see all the response headers that were given. And if I were to change this to a GET request, it would say method not allowed. So I have to return here. Otherwise, it'll fall down to post was accepted. Now, one curious thing about the Go multiplexer is that if I were to make some completely random route request over here, right? Obviously, test whatever doesn't exist in our routes. But if I call it, we can still see hello web. And the reason for this is that our slash over here acts as a catch-all, which basically means that if there's any route which is called, which is not registered on this server mux, it'll all be handled by this slash over here, right? And we can change that. We can say, if if the route that they called did not exist, I don't want them to see this slash response. I want something else. So you can say that if r.url is not equal to slash, right? If r.url.path is not equal to slash, we can say that, okay, this was not found, right? And we can pass in our response writer and our request, and we can return, right? So now if I were to run this and I were to pass it here, you can see we get the 404 page not found error code, 404 the response code over here as well. And this is basically how you can define that, okay, if they call a route which doesn't exist, I want them to see page not found. Now, one thing over here is that currently when we call fprintln here, right, what this is doing behind the scenes is that it's basically writing to the server, writing to the response body, and it's also sending a 200 error code, which basically means that the response was successful. By default, when you call this fmt fprintln, or the more common, the other one is w.write. This is also used occasionally, right? So if I were to say hello, these two are basically equivalent, right? And for example, what we can see here is that by default, 200 response code is sent, right? But what if we don't want 200 response code to be sent? Here we were sending 404 because this is a pre-built function, right? This is already called. So behind the scenes, it sets the value, the response code as 404 and returns it back. That's how we are seeing 404 here. But what if we want to set the response code ourselves, right? So I'm going to change this to w.write as well, right? And I'll say this. Oh, and by the way, this basically means a slice, right? These two symbols you can see usually in arrays in C and C++. Python uses lists. In Go, we have both arrays and slices. And arrays are equivalent to the C++ arrays where you can't increase their size. But a slice is more like a Python list, right? It's more versatile. It's easily modifiable. And so this basically declares a slice of bytes and inserts the values hello web into this. Right. So here what we're doing is we're sending method not allowed, and this by default sends a 200 error code, right? So if we want to change this, we can say w.write header. And here you can see it's asking me for a status code of int. Now the status code for method not allowed is 405, right? And if I were to run this right now and call the get request over here at test, I would now get a 405 method not allowed response, right? And another thing we can also do is that instead of having to remember the error codes for every single status, Golang's HTTP package comes with a set of variables, right? So we can say status method not allowed. And this is basically an integer, which is 405 over here, right? So it's basically doing the same thing, except it's more verbose, right? Oftentimes, if you're looking at some error code in the code and you see, okay, I got an error response of 312, but I don't know what that means. So you look in the code and you see, okay, status something, right? Whatever 312 is. So this is how we can write custom, not custom. This is how we can change the response code that we want to send from our server, right? Now, what if we also want to tell the client that you have given a request with get, which is not allowed? I'm going to tell you it's not allowed. But I will also tell you what is allowed, right? We want to mention to the client that, for example, post is allowed to this route, so that the next time when the client calls the server, it knows that, all right, post is allowed here. I have to send a post request. And we can say header.set. And if you remember, headers are basically key value pairs. So what we're doing here is we're setting the allow and we're saying post, right? So now when we run the server and we say, I want to send a get request to this, it'll say also allow post. This is the header that is allowed. This is the type of request that is allowed on this route. Okay. So this is how we can change the response code. This is how we can add headers, custom headers to our response as well. Now, oftentimes what will happen is that write header is called only once, right? You can only call it once. Once you send the response code, you can't go later and change it, say that, okay, before it was not allowed, now it's allowed. You call it only once. And if you have not called it by the time you call write, then write will send you a 200 OK message. So what people often do is that they combine these two messages, these two commands, right? They'll say, okay, we'll send http.error. And what this does is it combines these two lines over here. It says that, okay, I want to send I want to send to W an error string of method not allowed. And I want to say the code that's supposed to be sent is http.status method not allowed, right? And so this is basically the same thing as these two, all right? And this is a more shorthand method of expressing this, right? So now we're going to talk about path and, first I have to mention that all of this stuff over here is how Golang used to work before 122. So the version we're on, you can see in the corner here, is 122. This is all pre-122 stuff. Now, if you are on 122, you can just type post/test and it'll recognize that I want to send that only post requests are allowed here. So again, if I were to rerun the server and send a get request, it would say page not found, because this time it's not saying method not allowed, because technically the way we've registered this route on the server mux is only post requests, right? So a get request doesn't even show up. They're like, what is the get request? Which route is it supposed to go to? Okay. So this is how it's now done in 122. But before, you used to do it like this, right? You used to check the method and say if it's post, and then basis on that, you would write an error response. So I'm just going to change that back. Right. So we're now going to talk about how you can access query parameters, right? And if you recall, query parameters look like this, right? ID equals something, right? But in the registration, you'll not do any of that. You'll just say /greet. Sorry, not /greet. We'll say /by. And we will call this by function. And you'll say here that, okay, we have a function by, right? And we want to access this. We want to access the query parameter for this by. So what we'll do is that we are going to access an ID, right? And the way this is going to work is that we're going to say r.url.query.get, and we're going to give in the query parameter name. So we're going to give ID is equal to r.url.query, and we're going to say, okay, I want to write to W. I want to say hello. Okay, wait, we can't do that. I'll use fmp.fprint. Okay. So the reason I wasn't doing that earlier was because I have to pass in parameters, and that would make me create a string earlier. So this is a simpler way. We're just going to say fprintf, which is formatted string, and we're going to say W. We're going to say by. This is by, and we're going to pass in this ID over here, right? So we also need to include the \n, since fprintf is a formatted string, so we have to be a bit more literal about our new line. And so what this will do here is that if I were to run this, if I were to run the server and I were to call a get request with by question ID is equal to 10, right? You can see it says by 10, right? Now, this is often used in applications where you want to get a specific ID of perhaps a customer, perhaps some movie, some book, whatever it is that you are querying for. And oftentimes what you'll want to do is you'll want to have certain checks on that query. Like, for example, if I'm getting an ID over here, I want to make sure that the ID is actually an integer and not something like by hello, right? I want to make sure that this is actually an integer. This is a valid integer for an ID. So I can't say -1 or -2 either. So here, what we're going to do is we're going to add strconf.atoi. And this is how we convert a string to an integer. And you'll see that it's giving me an error, and it says that one variable, but it returns two values, right? So we'll just add a value here. And this is how Golang error handling works. In Golang, we don't have try-catch or any of the similar paradigms that exist in C++, all that stuff. What happens usually is that if a function can error out somewhere, what it will do is it will return an error to the function. It will return an error along with some information, right? So what strconf.atoi is doing, it's converting the string to an integer. But if I were to pass a string to it, it obviously can't convert it to an integer. So it's going to send me back an error instead. And that is what's going to be received in this variable over here. So what we want to do is we want to check if error is not equal to nil. And this is going to check whether we received an error while we were calling this function or not. And another thing we want to do, as I mentioned before, as an ID, we can't have negative values. So we also want to check is the ID less than 1, right? And if it is, we'll say, we will write, sorry, we will write that, okay, this is error. And we'll say, for example, internal server error, right? And then we will also return. Otherwise, it will come back here, right? So now it's giving me this suggestion to change it to %d because now it knows that ID is an integer. So this is how we can retrieve query parameters from our path. And you'll see now that if I try to say, okay, ID equal hello, it's going to give me a 500 internal server error, and it's going to say the word error over here as we defined it here. And if I were to also send a negative value, it would give an error. And later, when you create more sophisticated APIs, you will obviously differentiate between an internal server error versus a wrong parameter being sent to the server. That is what error codes are for. But for now, for demonstration purposes, this is fine. We can just say that your request was not handled, right? And the last thing we need to talk about here is path parameters. And this is something that was recently introduced in version 1.22. Before that, you would have to use a framework to easily get path parameters, or have to trim the string and perform string manipulations and get it from there, which is not really how a backend application should work, in my opinion. So we'll say that, all right, we'll just say movie, right? And we want to give an ID over here. So we'll say, this is how we'll define our path, and we'll say movie. This is the handler. If you recall, this is the function that we are creating. So we will say func movie, and we'll add WR. WR, by the way, is a snippet in Golang so that you don't have to type out http.response writer, http.request every time you're trying to make a handler. You can just type WR and it'll fill it in for you. So what we can do is here, we want to get this path value, right? So we'll say r.path value. And again, this is something that was made in version 1.22. If you're on version 1.21 or before, this will not exist, right? You'll have to do some other methods. And we can say ID is equal to r.path value ID. So this has to be the same over here because this is a path variable. And we will say we'll call fprintf, and we'll say movie number, right? And now when we run this server, we can see a get request to 8080/movie/10, and it'll give us movie number 10. And similarly, everything else is the same: HTTP 1.1, 200, date, content length, content type, all that stuff, right? So this is the basics of how backend applications are structured. They consist of a server mux, which basically tells the application that for this route, I want it to be handled by this function. And each function takes in a response writer and a request. And the reason for this is that what we want when we create a handler, we want some specific stuff. We want some guidelines, right? We want the writer that we have to write to. We need the request as well for us to perform information on it, for us to perform stuff on the information that's being given. So this is the pattern here that is often used. And the next thing we're going to talk about are interfaces, which ties into what exactly handlers in Go, how they're represented in Go. So if I go back to the slide, you can see interfaces. If you've come from different languages, it might be different. Golang has a slightly different interface implementation. But an interface is basically a blueprint, right? Or a template. And it consists of methods over here. So any structure which contains those methods automatically satisfies the interface. Generally, in other languages, what you have to do, you have to explicitly state that this structure satisfies this interface. But in Golang, that's not how it works. You can say that as long as I have this method over here, this is satisfying the interface. And so if we were to make an interface which consists of method 1, and you had a structure which consisted of only method 2, it would not satisfy the interface. But these two over here, this one consists of method 1, this one has method 1 and method 2. So it's not necessarily that only method 1 has to be present. You can have method 1 as long as any number of methods that exist. And a common use of the interfaces is actually over here in, for example, the writer in http.response writer, because when you call fprintln, it wants to know that what it's writing to can actually write something, right? So how does it know that? It can't list all of the different types that actually write something. So what it does is it asks for an interface. io.writer is an interface that is predefined in the Go language, and it basically consists any object which can write has to satisfy this interface for fprintln to work on it. So here, http.response-writer is a structure that contains the write method. And because of that, it satisfies the io.writer interface. And therefore, anything that works on the io.writer interface will also work on this http.response-writer, which is how we can pass W in this fprintln function. And so we come to the point of what the handler interface is, right? What happens when you're calling /greet? It sends it to a function which performs something, and it handles that /greet. And a handler interface has to basically consist of one method only, which is serve http.response-writer star http.request. Star over here is a pointer, right? And like I said, like it's the same as C, basically a pointer to the memory location instead of the object itself, right? So we can see that in our function over here, we are sending in http.response-writer, we're sending in http.request, but there's no mention of serve http, which is over here. And the reason for that is that we don't want to have to create a method. We don't want to have to create a structure and then define this serve http method every single time we call a handler, right? So what we do is that we create a serve http function, and the serve http function just calls the function that we have implemented. So what it looks like is this is happening, but behind the scenes, what's really happening is that it's just calling the serve http method here, and this serve http method is calling our inbuilt function that we created. So it's a small little workaround in order to satisfy the handler interface, and this entire work is done over here by handle func, right? What it means is that it's going to convert greet to a handler. It's going to basically pass the information to a serve http function so that it can satisfy the interface. But that function isn't really going to do anything. All it's going to do is it's going to call greet, right? So it's a small shorthand workaround for how we can register handlers without having to constantly satisfy this interface all the time. So the next thing we're going to talk about is middleware, right? And middleware is basically any function which is called before the request handler. When you usually call a request, it goes to the server mux and it sends it to the greet function. But what we can also do is oftentimes we want to pass it through some checks, maybe some logging function before the handler receives that request. So this is an example of middleware. You have the server mux, you have a middleware function over here, which can do many things. Most common use cases is logging the request that you've got, and also checking, for example, in actual applications, whether the user who's calling that request is authenticated. Do we know the user? Do we want to expose private information to this user? All that kind of stuff can be defined by the middleware, because there's no point in sending a request to a function if the user is not allowed to access that information, right? You don't want that happening. You want to make sure that the requests reaching our function are called by users who are actually able to reach that function. And so this is how the flow looks like, right? Middleware is in the middle, and it's in the middle of our server mux and our handler, so that any request that comes to our handler, it first goes through our middleware. It's like a small barrier at the gates, like making sure that everything that comes into the function is properly checked, right? So we're going to create a small middleware function over here, and we're just going to demonstrate how it works, right? So I've made one over here. We're just going to copy this part so that save time. And we're going to say that this is our logging middleware, right? And what it takes in is an HTTP handler, and it sends up and it returns an HTTP handler. So we're just gonna, yeah. So in backend applications in Golang, it's basically a chain of handlers, right? First, you reach the mux. It goes to a middleware, which passes it maybe to another middleware, or maybe it just goes directly to the handler. And all of these satisfy the serve HTTP interface that we talked about earlier. And also another thing here is that in listen and serve, if you see, currently it's giving me an error, but if you were to see in listen and serve, it's actually asking for a handler. And the reason we can pass in our server mux over here is because mux also satisfies the handler interface. So interfaces are really useful when you want to have multiple types of structures performing one task, like when you want all of them to satisfy a certain condition, right? You don't want to define that, okay, if it's a mux or if it's a handler or if it's a middleware, then they can all fit here. You just want that, okay, anything which satisfies the serve HTTP interface will be allowed in this parameter here. So we're gonna uncomment this, and we're gonna say that, okay, this is our log middleware. It's taking in a handler, it's sending out a handler, and what it's returning is this http.handler func, which, as we discussed before, it's going to create this function that we're defining here, and it's going to convert it into a handler so that we can satisfy the serve HTTP interface, right? So we're just going to say log.println, and we're going to print the path. So the simplest logging middleware ever. Any request that comes to the server will be logged. You'll know what the path was called. And we're also going to call inside here next.serve HTTP. So you can see it's auto-completing for me because next is a handler, and the handler has to satisfy this serve HTTP. And we're going to pass in this W and this R to our to the this thing handler here, right? So this is also right. So similarly to how there's a chain of handlers, right? You can see there's a chain of handlers here, and W and R, which was our response writer and the response body structure, they're being passed throughout the chain. First, they reach the mux here, and then they get through the middleware, then they get through the function, so that it's the same. So that our handler, our middleware, they all have access to the same information. And these two values are just constantly passed further down the chain. And right now it's saying log middleware is unused. So let's change that. Instead of passing in just our mux, we're going to say log middleware, and we're going to enclose the mux within this, right? So This entire thing returns a handler, which as we've defined here. So that's how we can put it in a listen serve. And this is basically saying that, okay, you have the server mux. Before calling the handler inside, I want to log this middleware. I want to log the path that was called. So what we're going to do is we're going to read on the server and we're going to say curl.exe get movie 10. And you can see over here, we got a simple logging function /movie/10, right? This was the path that was called. If I were to say /movie, if I were to say, oh, also, you can notice that /movie, just saying /movie was errored out because we've defined movie here to compulsorily require a path at the end. So just /movie doesn't work, right? And then we can also say that, okay, for example, if I were to say test, right? /test is being logged, and it doesn't matter what the response of the body is. Before the body, before the request is responded to, we are first logging it inside our middleware. And generally what you'll see happen, there'll be more information inside this. There'll be perhaps the method that was called, the body that was sent. And all of this will generally be put in a file or something so that later you have access to the logs and what people are calling on your API. All right. So this is a small application that we've made, simple demonstration of how HTTP requests, how backend basically works in what do you call it, in APIs in Golang, right? Generally, what will happen is that in major applications, you'll have a database as well. So a common practice and a good practice is, for example, in this buy, right? You want to make sure, for example, if you were to send in an ID and you had a database consisting of IDs and names, you wanted to get that name, right? You would not connect to the database inside the handler and get the name from there. You'd instead pass it to a different function somewhere else, which does all of the business logic for you, right? And this is a common practice because when you're writing tests, uh, it's better to separate out the business logic from the handler, right? Because the handler is taking in HTTP requests, taking in information, but we just want to test the information, right? We don't want to test whether the information is coming in or not. So that's why there's the small separation of business logic and handlers, right? So this is extremely simple one that we've gotten set up here. And so now we can move on to a bit more advanced Golang, right? Which is concurrency. I mentioned concurrency earlier in the beginning as one of Go's strong points. And today we're going to talk about why that is. So concurrency is executing multiple tasks at the same time, right? Oftentimes what you'll have when you have a heavy process, you don't want the program to be stuck on that heavy project, on that heavy process. You want to call the heavy process and you want the program to continue until the end of the process, until like while this heavy process is moving on to the side, right? So instead of having something like something happens, you call the heavy process, you have to wait here for maybe 5 seconds or whatever the process, however long the process takes, and then only you can continue. Instead of that, you can just be like, okay, I'm here. I'm going to call this heavy process to the side and I'm going to continue on. You work in the background, right? And if I were to give you a real life example, it's like if you had to warm your food and you put it in the microwave for a minute and you did nothing for a minute instead of, I don't know, maybe you'd scroll a couple of Instagram reels on in the meanwhile, but you were just standing there because you can't do anything until your food is done, right? So this is the kind of same logic that comes in programming, that when we have heavier processes, we want to execute them in the side. We don't want to wait for them to get over. And we're going to talk about how that works in Golang later on, right? So for example, if I were to close all of this and okay, so here I've got a very simple program which calls a count function, right? I have a count function here, and I have this for loop, which starts at 0, from it goes to 5. And what it does, it just simply prints the number here. And what I'm doing is I'm calling count, right, this function, but I have this go keyword over here. And the go keyword specifies a go routine, which means that I want this count function to be run in the side. I don't want it blocking my main program flow. I want it running in the side while I do other things, right? So I'm going to clear all of this out, and I'm going to say I'm going to run this program here. And you'll see that nothing happens. And the reason nothing happens here is because the way the Go compiler works is that it starts at func main, and then it calls count to the side. It says, okay, I don't need to stop here. I've called it to the side. I can continue. And sees another go count. It calls it to the side. And then it continues, and it sees that nothing's left. So the program ends. And the program ends before the side processes can even process their own function, right? So what's happening here is that it's calling the function, but before this function can even do anything, it realizes it's at the end and it stops. And so it kills all the go routines, and so nothing gets printed. So a simple fix for that is to just make it sleep for a couple of seconds. We're saying, okay, wait here for 5 seconds. And now when I run this, you'll see it's printing 0 to 4, 0 to 4, and now it's waiting before it ends. So I mentioned that you want to call processes that are running for a long time in the side. And the point of this would be if I were to print 0, like the responses should be interleaved with another, right? Because they're both technically working at the same time. So why am I getting 0, 1, 2, 3, 4, 0, 1, 2, 3, 4? And the reason for that is simply because by the time this gets called, this entire function is already over. So by the time the second go routine starts, the first go routine has already finished, and you can't really see that display of interleaving the responses here. So how we can change that is we can make the go routine also sleep 1 second every time it prints something, right? And this is basically a simulating some difficult task, right? Some heavy process task, which will take some time. So it's happening in the background. And now what we can see is that it's printing 0 and printing 0, and then it's waiting for a second, 1, 1, 2, 2, 3, 3, 4, 4, and then it ends. So like this is how we can wait for programs to end, right? How we can wait for our go routines to finish. But so this is a very simple way to do it. But what if we don't know how long this will take, right? What if this time.sleep was actually 10 seconds, and we defined here a time.sleep of 5 seconds, and we were to run this? You would print 0, and before it can even print anything further, this time.sleep ends and the program exits. So you can't define how long the program is supposed to sleep. What we want is a better way for us to know when this go count has ended. And this is where what's called a wait group comes into play, right? So I'm going to define a wait group over here, right? And this is of the package sync. It gets auto imported, and it's currently giving me an error because I'm not using it. But if I were to say go func, right? So here what I'm doing is I'm calling a function, and I'm going to, instead of calling count directly, I'm going to call count inside this function. And what I'm also going to do is I'm going to defer, sorry, first let me duplicate this. Right. So what I'm doing here is that I'm calling a function asynchronously. And then inside the function, I'm calling the count. And the reason for this, we'll see in a minute. But the point of a wait group is basically to keep track of how many go routines are running at a specific point, right? We want to make sure that when the program exits, all of the go routines have ended. All of them have finished with their task, and we don't want to exit prematurely. So what we want to do is we want to say, okay, we are having two goroutines. We can see two goroutines are being called here. So we are going to add two, right, to this WG. And what we're going to do at the bottom here is instead of time.sleep, we're going to say wg.done. And what this will do is it will wait for this, it'll wait for the wait group to go back to 0 when before it can exit, right? So it's going to block the program here until this wait group goes back to 0. And so how will it go back to 0? When we're calling this go func, the reason I changed this is because what I'm going to do here is I'm going to add a defer wg.done. Sorry, this is supposed to be wait, my bad. I'm going to call here wg.done. So wg.done will decrease 1 here. And we're going to do the same over here. Now, what does defer mean? Defer is basically a keyword in Go, which means at the end of the function, it's going to call wg.done. No matter what happens in count, at the end of the function, we are going to call wg.done. Now, since this is a 2-line function, I could have just done wg.done at the end. But generally, it's good practice when you need something that has to be done, no matter the result of the function, to put it in a defer so that you can put it at the beginning. You know that it's there. It's very common for people to forget to add this kind of commands, right? And so what we're going to do here, we're going to defer wg.done, defer wg.done. And so what it's going to do is it's going to count. We're going to change this back to, we're going to remove this time.sleep actually. And we're going to say that, okay, once it's done counting, then decrease 1 from this wg here, and then wait, right? So now when I run go run, automatically it prints everything. And you can see, again, it's back to 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. That's because, again, I removed this time.sleep. So this process gets over before this one is even started, right? So this is how we can use wait groups to decide when our goroutines are done. And this is often used when you don't know the number of goroutines that are called within your program, right? Somewhere in your program, you're calling goroutines here and there, and you want to, every time you do that, you'll add one, you'll wait, and the function, you'll defer wg.done. And you call the next one, you'll say add one, and then you'll wait. So this process means that at the end, it doesn't matter how many goroutines were called. What matters is that every time one was called, you added one. Every time one was done, you subtracted one. And you just have to make sure that it's 0 before you exit your program, right? So this is how concurrency works in Golang. And one common problem that comes up is that if I have this function over here, how do I communicate with it, right? This is a function that's running to the side. It's gone off. It's doing its own thing on the side. The main program has gone further down, and it wants to now communicate with this goroutine over here. So how can it do that? And this is where channels come into play, right? This is something that's in Go, right? A channel is basically a pipe, right? There's a lot of I feel that there's a lot of people who get confused on channels, but it's really quite simple. It's a pipe. You give stuff from one end, take stuff out from the other end. It's a queue over here. So one goroutine can pass information into this channel. Another goroutine will take it out, right? And what happens if you have multiple goroutines putting stuff in a channel, but only one of them is taking it out, right? For example, if this channel had a capacity of 1, right? If it had a capacity over here, and this goroutine gave information, and it filled it up, right? This capacity is filled up. Now, this goroutine also wants to give information here, but it can't because there is no space for for this goroutine to give information. So what's going to happen is that the goroutine flow is going to pause over here, right? Anything below that is going to have to wait until this command is carried out, until it can give information into channels. And this is for unbuffered channels. Buffered channels are slightly separate. Buffered channels have a capacity of more than one. So generally they'll look something like this, and they'll have more space over here for goroutines to give information. But if all of it is filled, then what will happen is that it'll block the goroutine over here, right? It'll block the flow of the goroutine, and it'll make sure that it stays there until that part is called. And a similar thing happens when you have an empty goroutine, right? So if this goroutine here is trying to take information from this channel and there's nothing in the channel, so it's not going to just skip over it and continue on. It's going to wait there because it needs information from this channel, and it's going to pause the goroutine here or the program, whatever it is. It's going to pause over there until it can get that information from the channel. So this is one property of channels that's extremely important to know. Unbuffered channels, especially where the capacity is only one, is that anytime you want to put something in or take something out, but it's full or it's empty, then your program will block. It will stop there and it will pause until it is able to take something out or put something in. And so while this might sound a bit problematic, it's actually really useful in helping us synchronize between goroutines, right? Because if you have two goroutines running at different speeds, but you need them to sync at one point, you can just make sure that the goroutine blocks at a specific point. You can just stop the execution at one point and say, okay, I want you to wait until I give you information that you're allowed to go. And so that's something that's really useful when you're writing asynchronous code. The ability to pause a goroutine that's happening on the side and say, okay, no, wait, I need something else to happen first. And so we can see an example of that. You can see an example of that here, right? This is a demonstration of how you pass information to and from channels. The arrows I showed here were actually kind of literal, because in Golang, you use arrows to insert information into a channel. And what's happening here is that you have messages, which is a channel, and the make command is basically a built-in function in Golang, which makes stuff, right? It can be used to make a slice. It can be used to make a channel as visible here. And you have to also define what kind of information the channel is accepting, right? Is it accepting a string? Is it accepting integers, booleans? What is it accepting? So over here, what we're doing is that we're calling a goroutine, and we're saying that in this goroutine, I want to pass in the word ping, right? Ping is being passed into messages over here. And so what we're going to do is that this channel is going to have a buffer. Like, this channel is unbuffered, which means that it has a capacity of 1. And this message over here is saying that, okay, I want to take information from the messages channel, and I want to put it in this variable here. So generally, what would happen if channels did not block, right? What would happen there? As we saw in this V1 here, usually what happens is that it reaches the end in small programs like this. At least it reaches the end of the program before the goroutine can even do anything. And that would be similar over here. If this was to be a unblocking command, right? It would say messages is make. It'll take stuff from messages, and if there's nothing there, it'll just say, okay, there's nothing there. It'll print out nothing. But that's not how it works in Go. If it's saying that it wants stuff from messages, it's going to wait there, and it's going to block the program and say, I want information from this messages channel. And so when the goroutine gives the word ping into messages, then it'll say, okay, I've gotten the ping here. Now you can continue, right? So when I run here, when I run channels, you can see that there was a pause over there and then ping was run, right? So this is a small demonstration of how you can insert information, take out information into channels, and and it also demonstrates the blocking capability of channels as well, right? And if I wanted to show what would happen if we couldn't block, I could make this a buffer channel, right? So if I were to make it 5, what does 5 mean? 5 is the size of this channel. This channel is saying I can take in 5 bits of information. And so what's going to happen is that this is going to, yeah. So this would actually cause information to go in, right? If I were to have multiple pings in here, right? So if I were to have multiple pings in here, then this would actually send in 2 pings, but only get out 1 because uh, like it's passing in the capacity of 5 means that it can hold 5 variables. So if I try to pass in more than 1, it's not going to block. It's not going to block this channel until it reaches its full capacity, right? And so another example we can see actually is when we want to sync our goroutines, right? So what we're going to do here is that this is another example of the ping uh, example I showed earlier, but it's a bit more simplified and more realistic, I guess, right? What we're doing here is that we're creating a channel. We're creating a channel which takes in Boolean values, and we're passing it to count. And count is saying, okay, I've gotten a channel, right? Again, remember that Golang takes the name first and then the uh, the type, right? So what it's doing its work here. It's saying, okay, it's printing out all the information, and then it's passing in true into the done channel. And so what we're doing here is that this line here is blocking the program. It's saying this program will not continue until I get information from done. And so when we go run channel sync, right, you can see that this time everything was printed. And if I were to remove this blocking operation, nothing is printed because the program ends before this count can even do anything, right? So this is an example of the importance of uh, channels and their blocking mechanism. It's highly useful in cases like this where you need a program to stop until something happens. And another example you can show, earlier I mentioned that wait groups are used for when we don't know the number of values, the number of channels that are, sorry, the number of goroutines that are being created, right? We don't know how many are created, so we do +1, -1 whenever they're made, whenever they're done. So what if we know how many goroutines are made, right? What if you want to keep track of that? What if each of them is sending back some data, right? So this is an example over here. What's happening is that similar to last time, we've created a channel called make chanboo, right? And what we're doing here is that we are creating here 5 goroutines, okay? So this for loop exists. We're creating 5 goroutines, and we're saying that, okay, when we're going to call this goroutine task, and we're going to pass in this channel done to it. And what this channel is going to do, it's going to say working. It's going to simulate any task by sleeping for a second, and then it's going to say done. And now done is going to return true. So, true is going to be put in the channel done. So now we know that, okay, this channel, this goroutine has been called 5 times, which means that theoretically there would be 5 trues inside this done channel, right? So what we can do is that we can make sure that 5 values are read from the done channel. And that's what this portion of code is doing here. We're saying that we want to read 5 values from done because we want to make sure that every time the Go routine is done, it's passing in a value and we're reading it. That means that we want to make sure that all the Go routines have finished their work before the program exits. And if we didn't do that, then like this program, like I said before, it would exit before this could even do anything, right? So we're making sure that all the Go routines have finished. And this is used in two cases. One is when we know how many Go routines are there. And the second case is the Go routine is returning information. So not always it'll be the case that it's going to print information. Actually, I'll run this first. Right. So you can see it's working and then it's waiting for a second and then it's done. So it's not always going to be the case that you want to print information inside the console, right? Okay. Usually what Go routines do is they're going to take in some information, they're going to return some information. When we want to retrieve that returned information, instead of having it return values and whatnot, you will pass it in a channel. And you can read that value from a channel because this is how Go routines can communicate with the outside world, with the programs, with other Go routines that have been called. It passes in values to the channel. This channel, which is shared by the main program here and this Go routine here, they can both read and put values inside the channel and synchronize themselves based on the requirements of the user or the person who is programming us task, right? So yeah, so this is how channels can be used to synchronize and how they can be used to communicate with Go routines with other functions that have called them. So with that, we come to the end of our session. And I hope every one of you learned something about Go. I hope you all learned something about backend. And if there are any doubts, you all can send them in the chat, right?